Welcome to our third year lecture in graduate combinatorics. Today we'll continue our discussion about graphs, matrices associated with them, and eigenvalues. So as you recall last time, we discussed how to a graph with vertex set V and edge set E, one can associate an adjacency matrix, A, and sometimes to make sure we specify which graph is associated to this matrix, we can just say A gamma with either between brackets or as a subscript. And this is a V by V matrix. So it's a square matrix like the Laplacian. And in the entry corresponding to the row X and column Y equals the number of edges from X to Y. And we gave these two examples last time where we have the graph gamma on 4 vertices, 1, 2, 3, 4, and you can see the adjacency matrix next to it. And then you have the graph gamma prime in blue with the same vertex set, and you have the adjacency matrix gamma prime. Now, what you notice is that the graphs gamma and gamma prime are isomorphic, but you see that the adjacency matrices, their adjacency matrices are different. However, the adjacency matrices of isomorphic graphs are related by the following property. They are similar by a permutation matrix. So this is the result that we sketch its proof via this example last time, that gamma and gamma prime are isomorphic if and only if there exists a permutation matrix P such that the adjacency matrix of one is P times the adjacency matrix of the other times P transpose. And for permutation matrices, P transpose is the same as the inverse of P. Okay. Now, from this result, what one can realize is that while the adjacency matrix is not necessarily an invariant of the graph because it depends on the labeling and so on, there is an invariant in the eigenvalues of these matrices because they're all the same. Since similar matrices have the same eigenvalues. Okay, so from now on, the convention will be that we will denote the eigenvalues of A gamma. One notation that we'll use will be lambda 1 in the non-increasing order. So lambda 1 is the largest, going all the way to lambda n, which is the smallest. And because the matrix A is real and symmetric, from linear algebra, we know that we have n real eigenvalues, including their multiplicities. Okay, and we'll denote them by lambda 1, lambda n. Okay. All right, now let's do some examples. So well, with that notation, I should also say that you can define the spectrum of gamma, or sometimes to be more clear which matrix we're using, we can say the spectrum of the adjacency matrix of gamma is this multi-set of eigenvalues. Eigenvalues lambda 1 greater or equal to lambda 2 all the way to lambda n. And sometimes we'll use in some situation, we can use a different notation, so you can have repeats in these eigenvalues, and sometimes we'll just use theta 1, theta t, the distinct eigenvalues of A, and m1, blah, 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 mt are their eigenvalues, their multiplicities, I'm sorry. Okay, so sometimes you'll see a notation of the form theta 1, blah, 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 theta t with multiplicity m1, mt. This is the, let's say, the spectrum, spec of gamma or spec of A. And so this would be spec gamma, let's say, in this notation. Okay, or sometimes the other notation that is commonly used is you write your eigenvalue θ1 and you write the multiplicity as an exponent. And you go like this, theta t mt. Okay, so let's do some examples. Before we prove anything, let's do some examples. Let's do, for example, the all one matrix, n by n matrix. This is a useful matrix to know its eigenvalues. And so you have one, okay, Jn, and it's clear that the rank of Jn is 1 because you have just the row space, or the column space is just spanned by one row. And that implies from linear algebra that 0 is an eigenvalue. The dimension of the null space of Jn is the multiplicity of 0 is an eigenvalue. So 0 is an eigenvalue of Jn with multiplicity n minus 1. Now, if you don't, this, you know, I'm using this result from linear algebra. You can realize this fact about 0 in a more concrete way. I mean, if you have the all one vector, the all one matrix, and I multiply it by a vector that has a 1 in one position and a minus 1 in the other position, what do you get? You will get the 0 vector, which is 0 times 1, 0, minus 1, and so on. So for any I and j that are different, the vector ei minus ej, choose, remember, it's you have the ei is the one that has a 0 everywhere except the one in the ith position, and the ej is the similar vector. So this vector, which at the end you can just write it like this: 0, 1 here, and minus 1 here. This is the I position, this is the j position, is an eigenvector of Jn with multiplicity. Well, forget about multiplicity. It's an eigenvector. Okay, I was confusing with eigenvalue. Now, so here I different from j, so you have about n times n minus 1 such vectors, but several of them are linearly dependent, and it's easy to show actually that if you pick some index, let's say 1, and you can do e1 minus e2, e1 minus e3, e1 minus en are linearly independent, and there are n minus 1 of them, so they will span the eigenspace of corresponding to 0. So we have you know, n minus 1 linearly independent vectors in eigenvector. So where is the remaining one? Well, if you take jn, and you multiply by the all one vector, you get n, which is n times all one vector. Okay, so what you get is that n is an eigenvalue with multiplicity 1, and 0 is an eigenvalue with multiplicity n minus 1. If you want to write it the way we did before, it's spec of Jn equals something like this: n with 1, 0, and minus 1, or you can write it spec Jn is, let's say, something like this: n with multiplicity 1 and 0 with multiplicity n minus 1. Okay, so that's a all one matrix. And now there's no graph whose adjacency matrix is the all one matrix, no simple graph. Okay. It is the graph with the, well, depends on how you count the loops, but let's have a first graph and we take the complete graph. Kn. We discussed this in when we did the matrix tree theorem. And now the adjacency matrix of Kn, it's easy to see it's Jn minus In. And from our work above, it follows fairly easily that the spec of Kn will consist of n minus 1 with multiplicity 1 and minus 1 with multiplicity n minus 1. So the eigenvalues will shift by 1. Or if you want to write it the other way around, spec of Kn is like this: n minus 1 multiplicity 1 minus 1 multiplicity n minus 1. And you also have the eigenspaces. The eigenspace corresponding to n minus 1 is spanned by the all one vector. Okay, spanned by that vector. And the eigenspace corresponding to minus 1 is the orthogonal complement of the all one vector. And I describe a basis over here for it. Okay. Now we'll learn some more techniques about how to calculate the eigenvalues of other graphs and the connection with the property. So, but let's start describing some connections between the matrices and the graphs. And the first result is the following proposition. Let gamma be a graph with adjacency matrix A. Then for any vertices x and y and any natural number L, if we look at the Lth power of the matrix L and we look at the entry xy of it, this entry equals, actually counts something, and it equals the number of xy walks of length L. Okay, so this is we'll see, it's a fairly simple result, but we'll see in a second how it works. If you want to play around with an example, take one of these matrices here. You can take gamma to be this one. 1, 2. Let me see how I. 3, 4. The adjacency matrix of it is here. 0, 1 here. And then 2 is adjacent to 3 and 4. And so you can take this matrix and you can try to calculate what is a square. Okay, what are the other things? So if you do a square, what do you get on the diagonals? And you get on the diagonals, it's 1. Here you'll get 2. It's actually not too hard to see that on the diagonals. You get the degrees of the vertices, and you get other entries in different positions. So a1, 2. I think you get a 1. A 1, 3. I think you get a 0. And a 1, 4. You get a 1. And then the other ones, a 2, 3. You get a 1. and A2, 4. You also get a 1. A3, 4. It's a 1. Okay. But if you do A cube, for example, if you look at it for on the diagonal entry here, you get I think you get a 3. No, I don't think I'm. I think you get a 0 here. Yeah, but for example, in the position 1, 2, let's see what you get. A 2, 1. So I will get the second row with this one, and I think you get a 1. But some other entries can get larger and so on. So now, so these results states that if you look at any of these matrices, for example, if I look at this entry here, 1, 2 being a 2, 1 being a 1, that means that if I start at vertex 2 and I count the number of walks of length 3 that go from 1 to 2, I'm going to get just one such walk, and it is, you know, well, it counts only the walk 2, goes to 4, goes to 3, goes to 1. Maybe let's do some other examples here. Maybe the entry here, A cube 3, 2. So that will be either way you can do it, but let's do row 3 of A times the dot product with this column. So how much we get? We get 1 with 1, 2 with 2, that's 3, another one. So I think that should be 4. And that counts the number of walks of length 3 that start at 3 and end up at 4. Okay. So how many such walks could you have? Well, you could do 3, 1, 1, 3, and then you go back to 2. You could do 3, 4, similar, 4, 3, and you can go back to 2. You can do 3, 2, 2, 3, and you can go back to 2. So these are these are 3, and then you can also do 3, 2. You go back to 4, and you come back to 2, and I think these are all the walks. Okay, so how does this work? Okay, why is this result true? Okay, so the proof, again, what we want to prove is that ALXY equals the number of XY walks of length L. Okay. So what we'll do is we'll use induction. So we use induction on L. So we want to prove this for any XY in the vertex set. Okay. Now for the base case, L equals 1, and what do we have then? Well, a to the 1 in XY equals the number of edges from X to Y, and that is actually a walk of length 1. It's the same as what you're counting here, and this is the number of xy walks of length L. So we're proving this result for simple graphs. Okay. Now for the induction step, let L be a natural number and assume that AL of xy equals TL of xy for any xy in V, where TL xy is the number of walks. Number of xy walks of length L. Okay, so we assume that is true for L. Now, well, first of all, let's figure out. Okay, let's figure out how can we get. So now let's take some x and y two vertices. So I want to prove. Let's write it here. We want to prove that AL plus 1 of xy in entry xy equals TL plus 1 xy for any x and y in V, where TL plus 1 xy is defined similarly to how I defined TL of xy. So let's think for a moment. If let's take two vertices, x and y. So x is here, let's say y is here. They could be the same, okay? But we want to understand, okay, we're doing a walk, something like this. To do a walk from x to y of length L, what do? You start at x0, and then you go x1, x2, blah, blah, blah. And you end up here at y, which is xL plus 1. Okay, so you have this sequence of edges that you traverse, and you end up in the L plus 1 edge in this walk is the one that has an endpoint y as a last endpoint. Okay, so if you look at this last edge here, the vertex that you visit, the other endpoint of this, so one endpoint of this edge is y, which is ax plus 1, and you have another endpoint, and that other endpoint is a neighbor of y. So I'm kind of stating the obvious here, but in order to get from x to y in L plus 1 steps or edges, you have to, it's the same thing as getting from x to a neighbor of y in L steps. So because, I just show you how it is to go from, in order to reach y in L plus 1 steps, you must reach one of its neighbors in the L step. And so these two things are the same. So what does that mean? This analysis implies that if I want to count the number of walks of length L plus 1 from x to y, that is the same as summing up over all neighbors z of y the number of walks of length L from x to z. Okay, that's exactly the consequence of what I just said. Because again, these L plus 1 walks from x to y, the collection of such walks can be broken down, can be partitioned into walks that reach a neighbor of y in the L plus 1 steps. So that's how you split them. And therefore, when you count the number of walks of length L plus 1, you will get this summation, because all these walks for different z's are different. You'll get a summation of TL of xz. All right. Now, from the induction hypothesis, what do we know? Well, we know that AL of XY or XZ equals TL of XZ. So if you plug that in here, you will get that this is a summation over Z adjacent to Y of AL of XZ. Okay, so I hope that's clear. Now, so that's on the, kind of starting with the combinatorics first. But if I look, for example, at AL plus 1 in the position XY, well, we know that AL plus 1 as a matrix is AL times A. So what does this equal? This equals summation over all Z. Well, let's use a different vertex here, maybe W in V of AL in the position XW times A in the position WY. Okay, you multiply the row X of AL by the column Y of A. But now this the matrix A is a 0-1 matrix. So the only term here that could possibly survive is the one where AWY is 1. And those are terms where W and Y are adjacent. So this is going to be a summation over W adjacent to Y of ALXW. But in that case, AWY equals 1. So you multiply by 1. So it's a summation of W adjacent to Y of AL XW. And now from the previous part, you remember we have TL plus 1 of XY. We had on the previous TL plus 1 of XY equals the summation over Z adjacent to Y of TL XZ, but this was the same as the summation of Z adjacent to Y AL XZ. So it's clear that this expression here is the same as this expression here, and therefore that implies that AL plus 1 of XY equals TL plus 1 of XY. So that finishes our proof. Okay, very good. Now there are many consequences of this result. So one of them is the following. It's again, I have a graph gamma with adjacency matrix. Okay, so let gamma be a graph, simple graph with adjacency matrix. A and eigenvalues lambda 1 all the way, I denote them like this, lambda a. Then if we count the number of closed walks of length L in gamma equals the moments of this, this is the L moment, so the sum of the L powers of these eigenvalues. Okay. Now, how how is this proved? Well, I'll give you the proof first, and then we can discuss it a bit more. So if we look at the closed walk, so from the previous result, so let's take L, V, and N. For X in V, if we look at the entry A in the matrix AL on the diagonal in the position AX, this equals the number of XX walks of length L. But this is the same thing as closed walks starting at X of length L. Okay. So that's from the previous proposition. So the trace of a to the power L equals the summation over all x in V of AL x x. And this equals, by our previous paragraph, the number of closed walks of length L. On the other hand, so A has eigenvalues lambda 1, lambda n. AL has eigenvalues lambda 1 to the L, lambda n to the L. And notice I don't put the inequality sign here because just because the eigenvalues are ordered in certain direction doesn't mean that their powers are going to be ordered in the same direction. But nevertheless, the eigenvalues are these, lambda 1, lambda n, lambda L. And so from here, what we get is that the trace of AL is the sum of the eigenvalues. So it's lambda n L. And so the trace is this, the trace is this. This means these two things are the same. Now, so you have to be a bit careful when we discuss these closed walks and this trace. So let me give you an example, what I mean here, for example. So in this situation, if I look at this matrix and I look at the trace of A cube, okay, this will count the number of closed walks of length 3. Now, the closed walk of length 3, it's the same as a triangle. But the closed walks here are going to be the following. So what are they? You have a triangle, you have one triangle, but as a closed walk, it can be counted in this form. 2 goes to 3, goes to 4, goes to 2. 2 goes to 4, goes to 3, goes to 2. Okay, so it's in both directions, if you wish, starting at 2. And then similarly, it will be the same method for the other, vertices. So you start at 3, and you get 3 goes to 4, goes to back to 3. 3 goes to 4, goes to 2, and go back to 3, and so on. So there's another one that I won't write, but what it gets is that this trace of A cubed will equal 6. So one triangle will have 3 possible starting points, and it will have 2 directions, clockwise and counterclockwise. So that gives you 6 ways. Okay. If you look at the trace of A square, this will be the number of walks, well, of length 2. And let me do it actually here because I'm running out of space. So if I look at trace of A square, the number of closed walks of length 2. But the closed walk of length 2 is essentially you have a vertex X, you go to a neighbor, and you have to come back on the same edge, come back. And if you count that, that is going to be the sum of the degrees. It's the sum of X in V dx, which is twice the number of edges. So we get the following consequences if we spell them out. For L equals 1, we get that trace of A is lambda 1 plus lambda n. It's a number of closed walks of length 1, but there are none, so that's 0. Okay. L equals 2, you get trace of A square equals lambda 1 square plus lambda n square. And this is going to be the sum of the degrees, and it's twice the number of edges. And L equals 3 is trace of A cube, lambda 1 cube, and lambda n cube. And here what you get is 6 times the number of triangles. Let's say T3. Well, T3 is bad because I use that. 6 times number of hashtag triangles. Okay. And you can continue this process, but it gets a bit more complicated. L equals 4, you can get trace to the A to the 4 is lambda 1 4 plus lambda n to the 4. But here, closed walks of length 4 can be various things, because you can, closed walk of length 4, it could be you start at a vertex, you go to a neighbor, you come back, and then you could go to a neighbor and you come back. So it could be something of the form x, y, x, z, x, and this y and z are neighbors of x, but they do not necessarily have to be equal. So it's the order pair y, z gives you a walk, a closed walk starting at x. So they will give you the degree of x squared, such closed walks. And then what else could you have? Well, you could have the ones where you have a cycle of length 4, and you start at x, and you can go clockwise, or you can go counterclockwise. And so you have two ways, but you can start off any of the other 4 vertices, any of the other 3 vertices of the cycle. So you get 2 times 4, the number of 4 cycles. So thank you. The trace of A4, it's a summation over x in B dx squared plus 8 times the number of 4 cycles. So I leave you to verify if that's right or not, but I think it is. So yeah, and I think there's some paper in which people figure out this higher powers, but it gets, like I said, like you see, a bit more complicated. It's very useful in certain situations, like random graphs, whatever those are, and this result about the closed walks and the sum of the powers of the eigenvalue can lead to quite strong results involving the eigenvalues of random graphs. Now, so I think I'll just discuss one example and then finish up. So quickly, let's do an example of the complete bipartite KAB, the complete bipartite graph. With A vertices in one side, this Ka equals 2, and B vertices on the other side, KAB. If you look at the adjacency matrix and you label the vertices on the A side first, you get this 0 matrix, which is A by A. And then here you get all one matrix, which has A rows and B columns. And similarly here you get JBA, and here you get a 0B. So, and if you wanted to be more concrete in the case of our example, what you get is these 2 vertices from A are not adjacent to each other, 0, 0, but they're adjacent for the 3 vertices across. And then here you have those 3 vertices adjacent to the 2 across, and then you have no adjacency among those 3 vertices. So that's how it looks like. So as you see, you have these big blocks, JAB here and the transpose JBA. They're not necessarily square. Okay. Now, how do you find the eigenvalues? So we can use the rank trick here. If you look at the adjacency matrix, the adjacency matrix is 2, because you just have 2 linearly independent rows or columns, and that implies that 0 is an eigenvalue with multiplicity, the number of vertices minus 2, so that will be A plus B minus 2. So we just have to figure out 2 other eigenvalues, and let's just denote them by theta and tau are the other 2 eigenvalues. So what property do they satisfy? Well, the trace of A is 0, and it's the sum of the eigenvalues. So it's going to be theta plus tau plus a bunch of zeros. So it's just theta plus tau. And also the trace of A squared is the sum of the squares. So it'll give us theta squared plus tau squared plus the squares of zeros. But here we get twice the number of edges, and twice the number of edges is 2 times AB. So we have this system, theta plus tau is 0. So that means that tau is minus theta, and you plug it back in and you get 2AB is theta squared plus, now tau you replace it by minus theta squared, so it's 2 theta squared. Let's just assume that theta is the one that is larger than tau, let's say greater or equal. And so in this situation we get that theta will be square root of AB, and that gives us tau minus square root of AB. So as a conclusion, the spectrum of the complete bipartite graph, it has 3 distinct eigenvalues: square root of AB multiplicity 1, 0 multiplicity A plus B minus 2, and minus square root of AB with multiplicity 1. All right, so we'll do more next time, and I will show you some results, combinatorial results, which can only be proved. So for which the only proofs that we know at this time are using eigenvalues of graphs.